Hello, everyone, and welcome to a buildingSMART webinar. My name is Jeffrey Ouellette. This is part of our 2022 Spring Summit. I'll be your moderator today. Today we're in the technical room talking about what we call past as precedent, where we're looking at what is happening in other domains. We've done this in previous summits where we're trying to get more perspective from what other industries are doing when it comes to handling large amounts of data and how we make use of them in different platforms, use cases, and everything. So our speakers today include Casey Mullen from Bentley and Arran Langmead from Epic Games. Greg Schleusner will be giving us a little bit of an introduction. We'll have a presentation from Casey. We'll have a bit of discussion from Arran and Greg and sort of cover this. We probably will only go an hour. We won't go the full 2 hours today. We will have available for Q&A. So if you notice that everyone is muted for the duration of the webinar, if you have any questions or wish to make comments, you'll notice that there's the comments section on the right-hand side. Go ahead and enter them there. We'd also like to bring to your attention, of course, this slide, that buildingSMART is committed to ensuring that participation in the development of standards is unrestricted and their process for adoption is transparent, and the standards are developed do not favor any particular provider, are open, non-binding, accessible to all. Please take note of our antitrust code of conduct. It can also be found on the buildingSMART website. So at this time, I'm going to hand it over to Greg.
Yeah, thanks for that. So like Jeff gave in the intro, today is a sort of continuation of what we've been doing in some previous sessions, which is really bringing in people that are both inside AEC, and I don't think we've done many outside AEC, but sort of Arran today is going to talk through some work on Unreal Engine, and then Casey's going to talk to iModel. But the point of bringing these here today is not to say that each one of these things are directly applicable to what buildingSMART wants to do, but I think some interesting themes. One of them came up in the conversation yesterday. We were talking about what a functional view of what IFC wants to do in the future, and there's a quick discussion talking about all web or files and stuff like that, and on the SQLite side of things, that's sort of the basis of iModel. It's an interesting compromise in being able to do two things good instead of trying to make a decision that only does one thing well. So that was one of the reasons we want to have Casey here today. And then on the sort of why show some work that Epic is doing is really that I think there's a notion that our industry sort of reuses technology and doesn't maybe take advantage of the newest technology out there. We're actually asking Arran to talk about one file per actor. I'm sure this will bridge into some other things in discussions, but really the idea there was it's a similar large data set that's built in a collaborative way. What are they doing to make collaboration easy? So that's one of the reasons we wanted to bring Arran in today. So we'll start with Casey. The floor is yours. This is a light conversation. We're not going to do much more than have you guys walk through your stuff, and we'll go through questions at the end. Thank you.
Okay. So let me know if my screen is showing up. Yep, I think I see it there. So good morning and good afternoon, everybody, wherever you happen to be. I'm Casey Mullen, I'm Information Architect for the iTwin platform at Bentley Systems. Going to talk about iModels, and as Greg pointed out, it's in the context of, might this be relevant for things that BSI is considering. So I'm just going to talk about some of the key drivers behind why iModels are the way they are, and along the way I will describe how iModels are and how they work, and then maybe make some comments about how this may relate to BSI concerns, and you can sort of be the judge as to whether any lessons learned from that. So in terms of the drivers, a sort of fundamental concept or contrast with IFC is, IFC, it tends to be about a data exchange workflow of different applications exporting some data and then other applications importing it on the other side, where we have a different focus in terms of our workflow of transactional interaction with shared data. So we are coming from the perspective of the application that's actually doing the authoring of the data, but and doing that in a create, modify, delete sort of way, rather than just a export, import, dealing with the data. And that perspective of the authoring application or other applications that are interactively updating shared data. So tracking changes was a concern from the outset. So we want to support a Git-like capability of working with design and engineering data. Tracking changes is just helpful from a logging or seeing what who has done what with the data perspective. And also, if you're trying to write software that's incrementally reacting to what has changed most recently, the change tracking is fundamental to that. Our applications need fast queries, including spatial queries of the data. So that has been a key concern from the beginning. We have to deal, like IFC, with a variety of known and unknown discipline domains. And by unknown here, I mean unknown to software, or at least unknown to the software at the time the software was written. So we write software that sort of can look at a data set and reflect on it and determine, what kind of data is in it, expecting to find data that we didn't, necessarily know about at the time the software was compiled. As Greg mentioned, we have needs to produce applications on the web, on mobile devices, on desktop applications, and to support cloud services. So we need something that can work in all of those environments. The productivity of our own developers, as well as third-party developers using our APIs, has been an important driver. And openness is really strategic as a company, basically because our own users demand it. People don't want their data locked up in a proprietary way. And so the openness is got to pervade what we're doing. And we'll see how that factors into some of our decisions. But so those are some of the key drivers. So what are iModels? If you're not already familiar with them, it's sort of, unfortunately, iModels are a misnomer in a way. When people hear iModel, they think, oh, it's a 3D model. I know what that is, but that's actually not exactly the case. So an iModel is a database that can hold many different models, and some of those models will typically be 3D models. We call them physical models because they're modeling the physical and spatial entities out in the world. But we also have 2D models that are typically drawings that may be schematic or physical layouts or scale drawings. In some cases, 2D models that are holding, let's say, the horizontal or vertical alignments associated with a roadway or something. So a variety of different kinds of 2D models. We also have models that are non-geometric in nature. One example of those would be a functional model in a plant, for example, modeling the functional, pumping and pipe flows to model a functional system. And then we'll take elements in the functional system and relate them to elements in the physical system that will be related to elements in a drawing that are depicting those physical and functional systems. So you get conceptually a whole graph of different interrelated models and elements in those models. In an iModel, we typically have, or it's always have one model at the top that we call the repository model that acts sort of like a table of contents for the whole thing. But it's important to not in your mind equate an iModel with a single 3D model, but it's really a database of interrelated models of different kinds. So that's an overview of the conceptual information in an iModel, but the way that software really interacts with it is via what we call an iModel briefcase. And the iModel briefcase is just a SQLite database that has got a representation of the information I talked about. So if you're not familiar with SQLite, it's not like Oracle or SQL Server. It's not a client-server database, but it operates sort of in process with local data. So once you have downloaded your iModel briefcase and have it local, then you have very fast access, and you're not competing with other processes to access the data. So that's very good, especially on sort of a mobile or desktop client. It has a very powerful SQL engine. We add our own little bit of syntactic sugar on top of SQL called EC-SQL that adds some better support for relationships, but it looks just like SQL, standard SQL 99 for the most part. SQLite scales up very well, particularly if you're on a device that's limited in memory. It's optimized for accessing data quickly off of the disk. So this is in contrast to technologies where you really have to hold the whole model, the whole project in memory in order to access it quickly. Well, that's not always possible for us. It runs on every platform that you can imagine, even some that are hard to imagine. And it's as open as you could get, supporting that openness driver. So it's beyond open source, it's public domain in the way it works. And it's got a built-in technology supporting change sets that are, as you'll see on the next slide, important for our tracking of changes and some of the things we like to do there. So we have this iModel briefcase, and if you can imagine, it starts out empty. If someone is creating new data and someone makes some changes, it could be one tiny change, or it could be a significant number of changes. And as a side effect of those changes, we can have SQLite generate this change set, represented by the little blue triangle there. And one thing I like to point out is that the granularity of that change set can be as big or as small as needed. So it's can span many different objects and their relationships, and so there's sort of transactional integrity around the change set that before and after the change set is applied, you have a consistent state for all your objects. But anyway, we could take that change set and we could send it to some central place, maybe in the cloud, for example, and start building a ledger of change sets. And this is basically just a little bit of metadata around a stack of SQLite change sets. And then as over time, more changes are made in the briefcase, generating more change sets, we can build up this ledger of change sets. And when we're done, we essentially have the information of the iModel in two places. Over on the left, we've got the iModel briefcase, which holds one version of the information in the iModel in a form that is queryable and editable. And then in this ledger of change sets, we have all of the information of all of the versions of the iModel, although it's in a form that you can't run a SQL query against this stack of change sets. So that's an interesting contrast. But you could check out a different briefcase, let's say only incorporating some of the change sets, and create a queryable version of a different version of the information in the iModel. So that's an interesting subtlety, you could say, about iModels is that you can have the information in iModel in the ledger of changes form, or you can materialize it in multiple briefcases. So you can take this ledger of change sets and host it in the cloud as we do. So that we used to call this service iModel Hub. Now we're calling it the iModels service of the iTwin platform. But this service essentially takes the iModel and turns it into a distributed database. And the way that works is that different clients, and they could be cloud services or mobile devices or desktop computers or web applications, can all get their own local iModel briefcase, and have their own copy that they can work quickly against. And if they make changes in any of those local places, they can generate change sets and then send them back to the central service to get added to the ledger of change sets. And basically, by exchanging change sets among each other, the iModel service is turning the iModel into a distributed database. And so that supports distributed workflows, and it is a scale out strategy in that all these different clients can be working very hard querying the data, and they're not really affecting each other except when they're exchanging change sets when things are being edited. So revisiting those drivers and how SQLite is relevant to them. Of course, the transactional authoring, SQLite is great for that. One thing I would point out in contrast to the data exchange workflows is that you can use an iModel to exchange data among applications, but like I said, rather than this export and import sort of paradigm, we have this shared pool of data that you expect all the parties that are trying to exchange data need to interact with. And so this really puts the burden, if a party is wanting to exchange data, they're responsible for doing an incremental update of the shared data. So they have to figure out exactly what's changed and what elements to either add or to update or to delete. And that is more work for an application than simply re-export all your data. But conversely, for any application that is trying to consume that data, it actually makes their life easier because rather than having to get an export from that application and an export from that application and an export from some third application and then try to reconcile all of that data, the iModel is sort of holding the data in a reconciled format. So as we showed, the iModel may contain multiple 3D, 2D, and non-geometric models that have sort of been pre-reconciled, you could say, and that are hopefully easier to consume. And also, as I noted, an application could be listening just for change sets and can interrogate what has changed. And so if an application is trying to react just to what's new, it makes their job a lot easier. So obviously SQLite is supporting our desire to do the change tracking. I talked about how it's doing that at an appropriate granularity. So it's not always just one object at a time, but it's also not, everything all at once. SQLite's great at supporting the fast queries and the spatial queries. In the session yesterday, the topic of graph databases came up, and I think Greg noted how you really want to look at not as much the technology, but what's the functional concern. And one thing we do get, so we have the objects, we have all the relationships, we can query that graph of relationships. So SQLite is not, a graph database and doesn't handle certain kinds of relationship queries perhaps as efficiently as a dedicated graph database, but it does have this change tracking capability built in at a low level. That's something you could always bolt onto a graph database, but may not be quite as efficient as what's built in to SQLite. And also the graph databases out there, if you try to get them run on your iPhone, so as we're trying to run on all these desktop, mobile, web, and cloud environments, it's harder to get a technology like that to run in all those places. And so that's another advantage of SQLite, that it runs in all those places, and as I noted before, it does the openness in spades. So stepping back a little bit to a broader context of iModels and digital twins. So iModels are a key part of our so-called iTwin strategy. So iTwin is basically our brand name for an infrastructure digital twin. And we think of that as implemented as a federation of different data repositories of different kinds. So iModels are one of those repositories, particularly for holding BIM-like, IFC-like data. But there's other kinds of data we call reality data, which would be photos and point clouds and meshes generated from photogrammetry. There could be sensor data, which is pretty simple, except that it varies with time. And so the sort of transaction model around sensor data is very different, just like the transaction model for reality data is different, and for iModels is different. And there could be these other kinds of data that, for one reason or another, tend to be kept separate or have a different transaction model. And I think Greg alluded to this yesterday as well, and said, do you want IFC to be one format to rule all those? And I think I echo his concerns there, in that you really want some higher level concept to try to take all these disparate kinds of data and learn how to federate them and correlate them, rather than try to have one format that tries to handle all of these things at once. So that's part of our strategy, and that is background for this next technology decision, which is to have iTwin.js, which is an open source TypeScript library, and I've got the obvious GitHub address there on the screen, and it's comprised of multiple different packages, some of them for accessing the iModel content itself in the form of the iModel briefcases, and there are different software components for helping to develop web, mobile, and desktop applications, as well as cloud services that access the iModel content, as well as being able to access other iTwin services that provide access to these other forms of iTwin content, like reality data that I mentioned previously. And so the iTwin.js is really, once again, supporting our goals of working on web, mobile, desktop, and cloud, and supporting openness and supporting productivity of Bentley developers and third-party developers. So the next and the sort of final topic I've got is BIS, or the base infrastructure schemas. And this is the thing that's most comparable to IFC itself. It is basically the data model, or the schema of iModels. And it is also designed with data authoring in mind. And that maybe has some subtle differences in terms of the degree of normalization, maybe less normalized data in BIS. And I would say that as we have been developing BIS, we pay close attention to IFC compatibility. It doesn't slavishly follow IFC to any extent, but when we're covering a domain that IFC is also covering, we know that the need to import and export from IFC is always there. And so that's sort of one of the checks, like, okay, does this work with IFC? Yes or no? And if it doesn't, we may need to rethink what we're doing. Greg also mentioned the sort of move towards modularity within IFC, and we've certainly adopted that approach. So the base infrastructure schemas is definitely plural, and it's a set of small modular schemas, so that at any given iModel, you'll find dozens of different schemas that have been imported, and each schema is sort of its own namespace. And these different schemas, we can roughly organize them into layers. We have the core layer that provides base classes for all the other domains. You could sort of think of it like the upper level ontology. We have a common layer that has schemas that are commonly used in across disciplines, or as base classes for multiple disciplines. Obviously, the discipline-specific schemas. And then the application schemas, and maybe application is a bit of a misnomer. These can be custom or extended schemas that are maybe customized per project, or coming as an export from some particular application. And what we sometimes refer to this as the dynamic layer, because these schemas are often dynamically generated from software. And one thing that I'll hit on a little bit later is that the schema language for our schemas, we call it EC schema. I'll show you some slides in a second. It's sort of the same. We use the EC schema to describe the core classes, and then applications can sort of auto-generate EC schema for these classes that subclass from the lower level classes, and essentially use the same schema language for the dynamically generated content as for the content that is known well in advance. But just sort of example, we have the BizCore schema that has a lot of our core concepts. And then in the common layer, there may be like a spatial composition schema, a linear referencing schema. And then the discipline-specific schemas will subclass classes from those other schemas. And then these dynamic or custom ones will further specialize those classes. So I'm not going to really teach you about the EC schema language today. It's been around at Bentley for maybe 15 years. Now it's open source with the rest of everything else. But this just sort of shows that it's a fairly straightforward objects and relationships kind of thing. It might be comparable to the conceptual schema definition language that you use in OData, for example. So you define a schema, you define classes, they have a name, they have properties and navigation properties with names and data types. It's got custom attributes concept. If you're familiar with .NET custom attributes, this is exactly stolen concept from .NET custom attributes for extending the metadata itself. It supports single inheritance and also defining sort of objectified relationships. So you can define a relationship class and define source and target constraints, and you could add properties to the relationship itself. We have online tools for browsing that kind of data as well. Another thing similar to the IFC strategy is we have the canonical form that we author as EC schema XML, but then we generate other representations of that as needed. So the TypeScript classes in our iTwin.js library are auto-generated from EC schema XML. We have other places where we generate JSON schema or XML schema. We have a cloud service that allows you to access an iModel as OData, and so we generate schemas for that automatically. These are not available commercially, but we've done prototypes where we've generated GraphQL schema or we've generated RDFS schema, but those, like I said, are not commercially available. And this is my final point that I sort of mentioned previously, that we, by using the EC schema language, we enable our custom or extended schemas to be expressed in the same language as our core schemas. So a little bit of analogy with IFC, it's sort of as if property sets were modeled using the same, UML and XMI as the core classes of ISC. And this is helpful in our software in that, whether it's a class or property that came from part of our core design, or whether it was auto-generated by some application that's trying to supply data, the classes and properties are all sort of first class classes and properties. And that means our SQL queries can operate against those extended properties and classes just as well as they can our built-in ones. And our software is written to just reflect on whatever schema happens to be in a given iModel, and they can treat those extended properties just in the same way that they treat the core properties, and that's all handled together. So I've got the URL to learning more about Biz in particular, but that's it for an overview of iModels and Biz, and you can draw some of your own conclusions there.
Thanks for that, Casey. This platform we're on this year, we don't see a number of attendees, so but we haven't had any comments come in. I guess we can take time for a few things. The one thing I didn't point out, but and this is very how do you say this? A personal opinion. The two things that I like about both the speakers today, both the way Bentley has implemented iModel, but also the way we'll see how Unreal from an editor perspective works. It's very much mirrors a software developer experience where you have you work on the data locally and then you distribute it centrally and then redistribute it back locally to collaborators. And I think it's an interesting, on top of the technology itself, it's an interesting paradigm to think about supporting, because there's this, fight, if you will, in the world to say if everything should be local or cloud or both. And I wanted to make sure I pointed that out because of the Git concept will come up today in both discussions, but also it's a design decision to support more than one in the iModel context versus one's first class and one's second class. I suppose is a good way to think about that. Is that fair, Casey?
Yeah, I think that's a fair assessment. There's a role for the centralized and a role for the distributed local.
Okay, Arran, I think we'll pass it over to you. You're sort of the when we got on the call, I think it's fair to be confused why Arran's being asked to present today, but I think we can talk through that. But I think from my interest, and I'll just say this specifically, is I dabble in Unreal. I don't make any games, but I use it for sort of visualization tests and these sort of things. And Epic is particularly open about engineering stuff, so I learned about this work watching a YouTube video, but also just the parallels of what Casey just talked about. So over to you, and go from there.
Sure thing. So I realized that I did say I didn't have anything to show, but I do actually have a project that I can load up and show, which might help. So I'm going to give that a go and make the tech person in the background have a heart attack because I said I wasn't going to show anything, but now I am. Right. Okay, so we're just going to go screen to and share and see if that works. Lovely. Cool. So the main thing that I'm going to be talking about today is one file per actor, because that's what I was asked to bring it to talk about, but it may extend a little bit past that, right? So we'll start talking about that and see how far we get. So I'm not sure how knowledgeable this audience is about game technology. I'm going to assume that it's maybe not as high as the people who I usually talk to who actively work in the games industry. But basically, Epic makes an engine called Unreal, and it's used to power all our games like Fortnite, and it's also used to power, kind of a lot of other games out there in the world. So we recently announced that we'd be releasing Unreal Engine 5, which is our newest version of the engine. And with that, we introduced a whole new bunch of features, one of which is called one file per actor. And one file per actor attempts to solve a big problem that we've had in game development, which is kind of building big worlds. And I mean like very, very, very big, kind of like 10s, 20s, hundreds of kilometers in diameter. This example that I have here is a measly 2 kilometers that you can kind of walk around and go explore in all, kind of all different areas. I realize my frame rate's not that great showing up on the capture, but you can kind of see how the kind of the size of that space. So the way that Unreal used to work with managing this, right, is that we would have all of our assets which would exist inside the content browser. So we have all of our meshes, our textures, our materials, the kind of all of the kind of the base content that we need for that, and that's stored kind of both locally for the user that's using it, and then also held on a Perforce server or other version control repository. And then we would have a level file, and this is the level file, right? And all that level file is doing is it's holding references to the points on which all of those things are placed. So if I have, kind of like a rock over here, it's holding transformed data and, kind of all of the rock information for all of the rocks that sit within this scene. And that used to sit inside a single, well, usually a single level file. So that would mean that level file would get quite big. And it would also create another problem, which is how do you share that level with multiple people? When you start building a big environment, you don't want to be building that entire thing on your own. You want to be building that with a team of people who are often, kind of different disciplines and different backgrounds. You have your environment artists, but you also have your gameplay designers who want to add, playable characters or non-playable characters to the scene. You might want to allow them to create quests and have audio designers putting sound in and background ambient noise. You might want to have VFX artists who are going in and creating all of this stuff. But because we only have one level file, and because it's a binary file at that, only one person can check that file out in Perforce and work on that file. And then once they're done, they check it back in. And obviously that is not really going to work. If you have a map like Fortnite, for example, you've got a couple of kilometers of space, but the Fortnite team is reasonably large. You need to be able to have multiple people working on that. So for Unreal Engine 4, we had a system called world composition, and we also had sublevels. And what that allowed you to do was to create kind of a nest of levels. So you'd have your master level, which would hold a series of sub-levels underneath that, and then you would hold the data within that, and people could manually check out those levels and they could work on that. So you might split your map by lighting, by VFX, by sound, by discipline, and then those different disciplines can work on that and kind of not get in each other's way while they're working. But that doesn't really work either, especially at scale, when you're working on those large things. And it's also kind of arbitrary, right? Like if I'm working on a section over here, kind of way off in the distance, why shouldn't I be able to, just work on this section while someone over on that side of the map is working on theirs? And that's where one file per actor kind of really came into its own. And essentially what it does is it takes all of the actors that sit within this level file and it breaks them out into a single asset, right? So a single actor, something that you can check out, you can modify, and you can do whatever you want to, and then check back in. So what that means is that this level that we're in at the moment is a single level file that we have, but the actual size of that level file is really small because it's not actually referencing kind of anything inside this level. They have their own actors and their own files that are stored on version control that are checkoutable and editable without you having to get in anyone's way to do so. And that's what the system that we've ended up coming up with to allow people to work on kind of like a single project without interfering with one another. So that's the kind of the basics of one file per actor. It sits in a hidden folder called external actors, and is basically a big long nest of folders and files that can be kind of managed and checked out by Perforce. So we only run this on Perforce mainly because of the checkout functionality that Perforce has. You can't, in games, a lot of the stuff that you're loading in is not diffable, right? You can't merge a texture or a model very easily, right? You'd have to build a tool that let you paint out the bits of the texture that you wanted to keep from the other person's change, and it would just be an absolute nightmare. So we have these hard files that you can't share the workload of that. You have to have a hard checkout. So once you've got this bit of area checked out, or you've got these trees checked out, no one else can make edits to them, and that way you're not again stepping on each other's toes or getting in the way of that workload. You're allowing other people to be able to work on those things, and if they try and work on something that's already checked out, it shows up as a flag and goes, you can't edit this thing because other people are currently working on it. And then once that's checked back into version control, or if it's reverted back to its original state, then someone else can check that asset out and work on it as they like. So yeah, that's the basics of it. With that system in place, it allows for a much greater amount of collaboration on these environments. They don't have to be big. They can be kind of quite small contained environments, or they can go up to kind of tens of kilometers in size, and the version control system will just check those files out. So the only real downsides to that is that you do end up with a very large number of files. So obviously one file per actor, it doesn't go down to every single file as an actor, because then we'd have kind of like a single file for every single blade of grass inside our game world, and that would be a lot of files. So while we do generally have one file per actor for assets that are placed in the world, so something like that you can be placed in, and that could be a single file. A lot of the actors that are within the world are placed down as instances, which is a much more simplified version. It's got that asset in memory, and it's going, okay, I want to stamp this around in a few places, and it will basically create a cluster of those instances. So you can kind of see this particular cluster here that I've got selected. That's going to be a single file, right? And that means that you can check out this cluster of, in this case, kind of grass and foliage, and then no one else can work on it until you've checked it back in. But it's not going to give you, the millions and millions of files that you'd end up with. So it tries to, kind of group them reasonably intelligently, so you aren't overlapping on too much of that stuff. And yeah, that's the system.
Thanks for that. There's two items I wanted to make the sort of conceptual link. One of the things that I think when I saw this, like the AEC space, there's actually sort of so many people that are coming together that authoring even subparts of data. But when you look at a system like this, and basically the level is sort of an empty array, right? If the flip side is like the engine parses all those files that are sitting in there, and then when you want to open this, it basically just instantiates into the scene array, I think is the way it was described on a talk you guys gave. Mm-hmm. But the point of pointing that out is it's an assembly of these things. There's only one, but in the AEC space, like the idea that you could have multiple assemblies of, just make a simple example. I only care about plants. There's no reason you couldn't make a level that just had plants. It wouldn't make sense in a game context, but in a sort of architecture, infrastructure sort of world, you can imagine, well, I want to assemble a level that or conceptually sort of one-time scene graph that brings all these things together, so I can sort of manipulate them and assemble them. But then also there could be a totally different version of that that brings those assets together in a different way. Again, it doesn't make sense in a game context, but from a capability standpoint, that's sort of one of the nice things I like about this. And then yesterday, I pointed out I'm doing some experimentation of doing rather straightforward ripoff of this idea is exporting file per element IFC files. And in my example, I'm actually using Git, but LFS, because of that sort of semantic versioning is not something that makes a ton of sense for things that it might make more sense in the long term for building data, but like textures and the things you mentioned, we don't have any kind of versioning in our industry at this point besides what, I think there are some sort of change viewers, but like actual version control besides the work Casey showed is pretty rare in our industry. And so just not trying to go for semantic, but just, that wall changed, that plant changed is a win for us. So that's the sort of conceptual link I wanted to make between what Arran's describing and, sort of the experimentation I'm doing on my side of things, I suppose. Any questions from anybody? Any cross reaction? I doubt, Arran, you've ever looked at iModel, and maybe Casey never looked at Unreal. So, anything relevant you see in this comparison?
Well, I certainly noted. It's funny how a lot of the problems are the same. When you look at a very large engineering project with all the different disciplines trying to edit things, it's very much like a bunch of game designers trying to edit a world. So there's certainly parallels there. You made a point about it's hard to diff and merge the assets in your world, textures, etc. So that is a key difference. And to the extent that our engineering information is a little bit easier to diff and merge, because maybe it's a little bit less visual, that's an advantage that we have and can take advantage of. But I would say that this approach of divide and conquer that you're doing, I think, is very pragmatic, and it's kind of the history of how it's been managed in the engineering world as well. Back in the Microsoft DGN paradigm, when people are working on a project, they'll often break it up into hundreds or perhaps even thousands of small DGN files. And the main reason that people are breaking things into smaller and smaller files is so that you can independently work on them and independently check them out. I will say that what we're doing with iModels is we're saying, like, okay, let's take all of those models and put them together in one database and do our change sets and change tracking. And to some extent, we're optimistic about being able to do the diffing and merging within that one database. And it's not easy, but it's largely doable. And in some cases where it's not, where you really, there is no point in having two different engineers modifying the same pump at the same time. They're not going to come up with a consistent result. We end up keeping a sort of locking metadata off to the side. And so before we allow the engineer to edit the data of a given pump or something, we check the lock table off to the side. And so they've agreed to all check the lock table first and say, like, okay, somebody else is modifying that pump, I'm just not going to modify it. So we're not enforcing that partitioning of the data by breaking things up into files, but we're sort of tracking on the side. Let's stay out of each other's way by consulting the lock file on the side.
And I think a lot of this stuff is, it's coming at a really good time, with the idea of the decentralized workspace. Like you're not sitting next to the person you're working with anymore, and that that does have disadvantages. So we need technology to keep up in that regard, so that we can still collaborate at the same speed as if we were working together. A lot of businesses now, they're going, well, if it doesn't matter where we work, then why can't we hire someone across the globe? Because we might as well just hire the best person for the job, regardless of where they currently live, and just deal with the time zone difference.
Okay. Well, we're not trying to fill any time, so the point of having these two guests on today were really to just explore sort of, I think, very relatable but certainly different worlds, but sort of to expose the sort of solutions they're trying to, or that are in place to solve problems. So as the session we had yesterday, we're sort of looking forward in the next year to do more of these, but sort of always looking back to a functional reason to describe what we should be doing in IFC as we move forward, and then sort of then coming up with the technical solutions. And to me, that's why I wanted to have this particular session, is to get the why we did what we did, and then that we arrived at the technology solution. So I really appreciate the two guests today. If you're interested in seeing more of these in the future, we'll have a TR4, I think, tomorrow, which will really, sort of lay out the roadmap of how we actually start to do more of these outside of just the sessions, and capture these functional requirements as we move forward in the next year. So again,
and then in some place in the near future, maybe over the course of the next month or so, what we'll try to do is aggregate all of those, either links to the movies themselves or links to the materials that we've seen in the past, and then things that we've seen today, so that we have sort of a centralized repository for those ideas that people can go back to, and we can link to and keep referencing to. Yep.
So that if you're interested in seeing more of these things, or bringing your own to the fore in the coming months, please attend tomorrow. Tomorrow will be very much just how should we do this sort of discussion. But again, appreciate everybody's time today. Really great to have the two guests on today, and that's it from my side of things. Thank you all.
All right, gentlemen, thank you. And this ends our today's presentation. We didn't have any other comments or questions that came through, so thank you all for joining us.
All right, thank you for the opportunity.
Bye.